We talked about the regioselectivity of E2 reactions. Remember that the reaction can happen and give us a Zaitsev product or a Hofmann product. That means the more substituted alkene or the least substituted alkene respectively. Now we're going to talk about the stereochemistry of those E2 reactions. That means how the atoms have to be positioned in space for this reaction to actually happen. So here, for the stereochemistry of for an E2 reaction to happen, two things have to happen. First of all, the atoms, that means the H that leaves and the leaving group that will leave, have to be in the same plane. So that means that you see here the hydrogen, the carbon, and the leaving group are on the same plane. And here they can also be on the same plane, right? So we have two options where they are coplanar. The, the second condition that they have to fulfill is that the elimination happens when those two atoms, that means the hydrogen and the leaving group, are 180 degrees apart. So that means that they are anti-periplanar. Anti-periplanar. There we go. So that means that if you look at it in a Newman projection, the H will be here and the leaving group will be here. Remember, these two are 180 degrees apart. So you see here, we see it with a different perspective. The base could come from the bottom and then the leaving group could leave, or the base could come from the top. You see here using this ball model that the base coming from top is not preferred because it's highly sterically hindered, right? And here is much better. So this is the preferred geometry for an E2 reaction to happen. They have to be in the same plane and the base has to come from 180 degrees apart from where that leaving group is. Here I'm showing it to you with a Newman projection. I'm trying to give you as many different perspectives for you to understand what's happening here. So here we have the leaving group and the hydrogen, so that's the beta hydrogen that is the one that is going to be taken away. And here we have them being in the same plane as well, but they are not 180 degrees apart. You see here, the base can come and will form, you see that the elimination will happen in the carbon-carbon bond in between the front and the back carbons, and then the leaving group will leave. So you see here, once the elimination happened, then all your groups will look like this, which is the same as having them in this projection right here. That doesn't happen when those two are eclipsed, because for the base to come from the top where the bromine is already there and it's bulky, that is very unlikely to happen. This has a particular importance in ring structures, because in ring structures you know that the hydrogens are either up or down. And so, for example, so in this reaction right here, you know that the chlorine is more stable being in the equatorial position. However, it will not react in this case, it will react in this case. Why? Because in this case, we have a hydrogen right there that is anti-periplanar to the leaving group. That doesn't happen right here. So I know it's counterintuitive because you know that this is the most stable one, but this is not the one that reacts. This will be usually the one that reacts. And I'm going to show you some examples for you to see that. I am trying to remove the autocorrect so you don't see those lines. I apologize for that. So so let's look at some of those examples. In here, we have the chlorine that it's on the equatorial. And you know that this is the most stable conformation, but here we have the chlorine that is axial, so that's the least stable. But in this case, the base can come from the top and can remove the Cl. The Cl will leave because that's anti-periplanar, and that will give us a double bond within the ring, just like this one. This conformation right here is not going to react. Now here we have another example where we have the cis and the trans, and again you can think about it in the same in this context, right? So here the chlorine is equatorial, so that's very stable, and here we have the chlorine that is axial, but you see this chlorine right here has a hydrogen 180 degrees, so that's the one that reacts, right? Seems easy, but it can get complicated. So let's look at one example here. So we have this molecule. We can have the cis one or the trans one, and we're going to look at it stepwise. So first, let's look at the cis conformation, and let's see what would happen in space. So you see in the cis conformation, both the chlorine and the isopropyl are in the same direction. So in this case, we have both of them being down. They are cis, right? So this is the cis. In the cis, chlorine is down, isopropyl is down. In this case, the base can come, grab that hydrogen that is 180 degrees apart, and then that will collapse and the leaving group can leave. And that's how we get this molecule right here. Now, for the case of the trans, in the case of the trans, we have the isopropyl pointing down and the chlorine pointing up. So here we have the isopropyl pointing down and the chlorine pointing up. You see, this is not going to react because there is no hydrogen that is 180 degrees apart from that chlorine. So there is no beta hydrogen that is 180 degrees apart. So even though this is the more stable chair, this is not likely to happen. Now, if we flip it, remember to flip it, we will bring number 2 down and bring, what is this, 5 up. So that's what we're seeing here. In the flip one, that it's very unstable, we have a chlorine and an isopropyl being axial. And that's very unstable because we have 1, 2, 1, 3 diaxial interactions all over. So remember, there's a hydrogen here interacting with a chlorine. There's another hydrogen there interacting with a chlorine. So that's very, very unlikely. So you see, that equilibrium will not be favored, but actually this is the ring that will react because we have the chlorine there, and that chlorine has one of the hydrogens that is 180 degrees and coplanar to that Cl. So then the base can come, remove that, and then the chlorine will leave. So here we see it, right? So the base can come and the chlorine can leave, and that's how we get the double bond there. So the regiochemistry is also important here, right? So just a reminder that we can get different alkenes when you have different beta hydrogens. So for example, this chlorine has 2 hydrogens that are coplanar. You see it has, I'm going to mark it here. It has one here, it's coplanar, and then on the other side, it has one right here. So that's why we have HA and HB, because we have 2 sets of beta protons. Now, if it goes through HA leaving, right, so we get the disubstituted alkene. And if HB is the one that leaves, right, so the base comes and removes like that, and the leaving group leaves, this is what we get right here. So HB is the preferred one because if we remove HB, we get the Zaitsev product. But if we remove HA, we get the Hofmann product, which is the more unstable. So here you have yet one more example of this that we've been talking about. So here we have the more stable conformation of this chair because the chlorine is equatorial and the CH3 is equatorial. And here we have them both being axial, which is something that makes them very unstable. Here the Cl has one hydrogen right there that can react, and so that's why this is the conformation that will react. But again, there are situations where there is only one hydrogen that is available to react. In this case, this chlorine right here only has one hydrogen, right? Because here you have one hydrogen and here you have a CH3. So in order for these to have two hydrogens available, you would have to have one here and one here. But because we only have one, when you treat this reaction with base, there's only one hydrogen available, and then that will react, giving us the disubstituted alkene, which is the less stable one, but it's the only one that could react. So in this case, because conformer D has only one beta hydrogen.